2 is a half. Is half an integer? No. Is reciprocal of 5 is a fifth. So in the integers, this class consists of only plus and minus 1. This class consists of only 0. So practically everything is in the middle. In the reals or the rationals, what is this class? Only 0. What is this class? Every non-zero real number has a reciprocal, which is a real number. So this class is everything else. So this one is as small as possible. That is as big as possible. And there's nothing in between. So you get this, and I've asked you to investigate this in various contexts. In particular, for arithmetic modulo A, can you see which numbers are invertible?
Would be the co-prime.
It's exactly the numbers that are co-prime, because that's what we did. The fact that if we're working modulo A, and we've got SA plus TB equals 1. So suppose A and B are co-prime. I said the immediate reaction is to write that down. If we working modulo A, then T times B is congruent to 1 mod A. We're pretending A is 0. So TB is 1, so T is invertible. So invertibility, the invertibility are precisely the numbers that are co-prime to A, and which are the ones that cannot be cancelled? Well, what can you tell me about these, 6 and 5, in relation to 10? They've got a common factor. 6 has got a common factor 2, 5 has got a common factor 5. So these are the ones that do have a common divisor greater than 1 with A. So it shows you that if you're working modulo A, all those that are co-prime to A are invertible. All those that are not co-prime to A, that do have a common factor bigger than 1, cannot be cancelled. And so there's no middle ground in that case. And so this is a very interesting situation to follow up as well. And I see that makes 6 o'clock. I wanted to do there's some numerical examples that you can do that come up quite often. But this idea that if B is co-prime to A, then you can always solve. Because B is invertible, you can always solve let's write it down quickly. If B is co-prime to A, or if A and B are co-prime, then equation Bx congruent to anything C mod A can always be solved. And this does come up quite often, even in simple cases, in first and second round. And why is that so? Because, as I said, SA plus TB is 1, and therefore TB congruent to 1 mod A. So you simply have to multiply both sides by T. TBx is congruent to TC mod A, but TB is 1, so X is congruent to TC. You basically, what did I say? T behaves like a reciprocal of B, so you're dividing by B. Multiplying by T is the same as dividing by B. So that can always be solved. And I'm going to give you one more, not perhaps quite so common. property when two numbers are co-prime. But if B is co-prime to A, then the simultaneous equations X congruent to some number, doesn't really matter what I call it, P. A. And X, same X congruent to Q mod B. So two equations in one unknown can be solved simultaneously. It doesn't matter what the right-hand sides are, provided that the two moduli are co-prime. And the trick is always, what's the first step in proving it? Oh, this is an important result. This is called the Chinese remainder theorem. And it apparently really is a discovery of the Chinese. Many of the other discoveries of the Chinese tend to be ignored as Chinese discoveries by Western people, but this, at least the Chinese get the credit for this. That's called the Chinese remainder theorem. It can be extended to more than two congruences, but doesn't matter. The important thing is for two. I can show you proof quickly. What's the first step?
Okay.
What happened when Pavlov rang the bell? The dog salivated. What happens if I say co-prime? What is immediately due? SA plus TB is 1. So that has to be the first step. Now multiply both sides by P minus Q equals 1. My hand doesn't always do what my brain tells it to. Multiply both sides by P minus Q. Now, if you rearrange that equation, this is an equation, these are real, still genuine integers. Then I always say you must be very careful to get them the right way. We can get, taking the Q to this side, Q plus this one, P minus QTB. Equals P minus Q SA. So this is a number, and this is your X. Because if we pretend that B is naught, then that bit disappears and you get X congruent to Q. And looking at that expression, it's the same number, so this is also your X. If we pretend that A is naught, then that disappears and you get X is congruent to P. And so there's the Chinese remainder theorem, proof of it, just a couple of lines. Simultaneous congruences, provided that the two moduli are co-prime. Well, my time has run out before my papers have, but never mind. There's still, so some of the things in the questions I haven't covered, but if you're interested in any of them, I've given you my email address there. You're most welcome to come and talk to me about anything. Anyway, we've got now until 7 o'clock. So I'll be here if you've got any questions you'd like to ask me now. So thank you all very much.